Welcome back to our Structure for and Interpretation of Computer Programs video series, where today we're going to try to translate this very Lispy functional code over here into some Java code. And we're going to see how we have to change our approach to make it happen with just the standard, obvious, introductory Java ideas. So it's going to be top down. Everything's going to be in this our main method. So it's all going to be considered side effect. No real outputting. So the first thing to do is what variables are we going to need to hold? The first thing to do is to declare our variables, coming up with the names. Well, we're going to store this the x, the number we're finding the square root of. We're going to have a double of guess, and remember, now that we're in mutability, our guess is actually going to be a variable. It's going to be rewritten. And how about we need to get that constant p that we used for precision in the previous video. So let's just say double precision. Here, what else are we going to need? A lot of these computations are going to be done in line. The average we're not going to write as a function. We're just going to do the arithmetic in line. Same with the squaring. The absolute value we're going to implement with an if right on the spot. This improve part of the procedure, it's going to be renaming the guess. So that will be another thing that's in line after a rename. This good enough is going to have to be a Boolean. So we'll do a Boolean good enough. And I think that might be it. So let's just keep going. Let's try. First, we're going to take a user. So we're going to get the value from a user, and we'll just call that user Isaac. Isaac equals new scanner system dot in. We're going to run this from the command line. We're not going to have a REPL like we did last time. So I think first we will get our inputs, right? We're going to use Isaac, this user interface system, to get the x that we want to use. So well, let's do it with a greeting too. We'll do system.out.println hello Isaac. Nice little new lines. New line here. Enter your input x. Nice. All right. Very good. And so x is going to, we can make it equal what the user inputs with Isaac dot next double. All right. So I'm going to try something we didn't do last time. Last time we hard coded our precision, how precise we're being. This time we're going to let the user decide. So let's do another note to the user. How precise shall we be? Which basically means to what tens place. And they're going to have to enter in. They're going to have to enter in a double. It'll be. We'll just look something like. It'll be of that form, or it could be really any. It could work with any double, but for it to actually get the desired effect, to make our guess more, that amount approximate, it would have to be like some zeros, and then a one's best, but it could be really any other. But anyway, yeah, the user will input that, and that's. Ooh, what did I do? Did I do precision equals precision? Come on, precision equals next double. All right. And that's going to be it with what the user inputs. So even though we're going to print out to the user, we don't need this scanner for that. So we can do Isaac.close here. Alrighty, so we have our X, we have our precision. So remember, we don't have recursion. Here we specified this really nice recursion. If you look over here in the closure code, and you can do recursion in Java, but I'm just going to show what you can do with mutability. And really, my goal is to show that mutability is not very civilized. It's once you come at it from an immutable situation, you have these beautiful recursions. You'll find that doing it immutably is just quite ugly by comparison. So let me. What are we mutating? We're mutating our guess. We need to initialize it. We need to start it at this 1.0. And I'm going to use it's called the do while form. It's doing a while loop where you test your conditional after you've stepped through the block of code once. It's just a particular way of doing while. So we're going to have do, and then here's our block of code. So what we're going to do is, and this was Newton's function, was this 0.5 times guess plus x divided by guess. That's really the average of the guess and the quotient of x divided by the guess. And this is Newton's function for improving an approximation of a square root. And we're going to assign that value to the name guess, which is going to overwrite this information, and we're going to need someone to evaluate how we did. Now, if you remember, the evaluation was this good enough function, right? And what's in this? We have an absolute value function, which means we're going to have to, what's absolute value look like? It's a conditional, so we're going to be implementing with a conditional, and it takes it tries to see how small is the difference between the square of the guess and our x. If we have a perfect square root, that'll be 0. How much can this approach 0? So this number is our precision. And this is our comparison that amounts to our good enough. And we're going to do that. Actually, it's going to be down here. It's going to be good enough equals basically let me just write in pseudocode the absolute value of the difference of x minus guess squared, but it's that absolute value. Is it less than or equal to? Or, I'm sorry. Is it strictly less than our precision? Right. So what do we need? What do we need to implement this? Well, guess is going to be guess star guess because we can't use that notation for exponentiation. There's a utility for exponent. I could just plug 2 into it, but I won't. Absolute value is a conditional function. I'm not going to be able to do that in line. It'll just throw me off. So why don't we have another variable? We'll use another name. We'll say we'll call it our measure of precision. So it'll be prec for precision and measure. All right, so we can what we can do is we can, inside the absolute value conditional, assign a value to this variable prec measure, and this code will have less of it in line, and it'll just be prec measure less than precision. That'll be true or false. The true or false is going to be crucial because basically we're doing do all this. Remember, there's code I haven't written yet. While good enough is still false. If good enough was true, we could stop. When it's not good enough, we have to keep improving our guess. So back up here to our if to implement our absolute value. The absolute value is going to be if our input, say our input y, is less than 0, then, we don't actually write then, but then what we do is we take -1 times y. And we're instead of returning it, because it's not really a function that returns, this is a side effect, it's not a pure function. So we're not going to return it, we're going to assign that value to a named variable. Forgot this. Else, which means, it's not strictly less than 0. Prec measure equals y. Just set it to y if it doesn't need to be, if it's already positive. You know your absolute value function. So there you go. Now we're not of course there because this y isn't right. That was just a placeholder name. The y is going to be, if you look over here, it's going to be this. It's going to be this right here. Let me just bring that in. So we just, translating the y value is going to be translating the, or we could just, why don't we just leave it? Let's do double y, and here we'll say y equals, and we translate this infix we translate this prefix into infix. I'm going to say guess times guess minus x. So notice the important thing, of course, is that I named it inside the loop because every time it goes through, it will overwrite this name with this value. And I think that's it. I think that is our code. I think that's going to work. So why don't we have some last note to the user? Actually, it'll be better. Check this out. We're gonna put our note to the user inside the loop, so that every time it improves the guess, it shows us where we're at. So let's say percent %d for double. Let me just do print f for formatted print. Times, or I'll just say squared, is approximately another double, where guess is the first double and x is second double. Cool. So check this out. Let's see how we do. Open up an E shell. Java compiler Newton's video.java. Java's file not found. Excuse me. All right. And we have some errors. Identify expected. New scanner system int, not int for integer, just in. Very nice. We have, here we need a semicolon. And look, we have another, when you're doing a do while, you gotta put the semicolon after the while. So, one more. Cannot find symbol. Next double. I need a T. Oh, so that's still not working. Why isn't it working? Oh, because I need Isaac dot next double. Yeah, I can't just have next double. It's next double that comes into this scanner. Hey, there you go. So let's see what happens. Newton's video. Hello, Isaac. Enter your inputs. X. 1024. How precise shall we be? Let's be down to the thousands, 10,000. And we have an error. Exception in thread main. Illegal format conversion. D does not equal java.lang double. What is D? I did not name anything D. Did I? No, not the percent %D, percent guess X. What line is that? 38. Line 38. It's in the, okay. Well, apparently, you know what? Maybe D isn't double. In my I consistently forget my my print F. So let's say, oh my goodness, I am so sorry about this Firefox window. It is absurd. We have what am I looking for? I'm looking for print F Java %D. That means double. That's not going to be there. Quick reference. Quick reference. That's what I'm saying. Flags. Exactly. Where are my flags? D is decimal integer. Byte, short, int, long. D is bad. I need F. I need F, of course. F for float. F for float, not D for double. Excuse me, I apologize. But you just saw some live problem solving. So I'm going to recompile after I save. Boom, we got that. And down there, enter your input X. 1024.0. How precise shall we be? We shall be 0.001. Oh, so this looks nice. I'm going to do it over again with some, with new line. Get that new line in there. So, boom, and boom, 1024, 0.001. Ha! Look at that. It goes down. See, it starts at after the 1. It first is around 512. Then it's around. Then it keeps getting closer and closer. Now it's approaching 32. It's arbitrary. Can be approaching 32 to an arbitrarily small rate. And we can just show if I say, oh, I don't need to recompile. I can just run again. 1024.0. How precise shall I be? 0. Really precise. It took a few more steps, and it kept going. It kept going so much that it wasn't natively printing that much. So I would have to tell it to print that much if I wanted it to, but it doesn't actually matter that much. There we go. This is our code. So that's just the standard like mutable data top down approach that's in it's in a lot of like introductory Java code, and as you can see, it is just it's just inelegant, and it's not like this great lispy wizardry mathematics we were doing earlier, and that's just immutability puts you in these situations with recursion and with pure functions that's just so much more satisfying than a mutable situation where you can get it done, but you're getting everything's a side effect. Nothing's really returned like the output of a function.